we are discussing propagation of plane wave across a media interface. In the last lecture, we derived the reflection and transmission coefficients for a uniform plane wave across a dielectric interface for two polarizations, the parallel and perpendicular polarization. We had seen that any arbitrary polarization can be decomposed into two orthogonal components, one which is perpendicular to plane of incidence and other in the plane of incidence, and then we can find out the reflection and transmission coefficients for these two cases, so that we can combine these two for any arbitrary polarization. Today we discuss a very important case, what is called the total internal reflection across the dielectric boundary. We have studied total internal reflection at the high school level, where we say, well, the ray is incident at an angle greater than the critical angle, the power is reflected back into the same medium. However, that understanding is rather a superficial understanding. Today we will do little detailed understanding of the phenomena what is called total internal reflection. We start from the Snell's law, and now you have derived the Snell's law, which says your beta 1 sine of theta I, that is equal to beta 2 sine of theta t, where theta I and theta t are the angle of incidence and angle of transmission, and beta 1 and beta 2 are the phase constants in the two media. If you write down this beta 1 and beta 2 explicitly in terms of medium parameters, we have seen that beta 1 is omega square root mu 1 epsilon 1 and beta 2 is omega square root mu 2 epsilon 2. So, the Snell's law which we have derived from matching the phase condition for the incident, reflected and transmitted waves, is valid for the fields in the two media for any value of mu 1 epsilon 1 or any frequency omega. So, if I substitute this beta 1 and beta 2, we can get in terms of this medium parameters the Snell's law, which is mu 1 epsilon 1 sine of theta I, that is equal to square root of mu 2 epsilon 2 sine of theta t. Now, while doing this, we simply match the phase condition, and we also said that the electric and magnetic fields have still the transverse nature. However, we have said explicitly that these waves should be traveling in the medium 1 or medium 2, and that is what is a very important thing which essentially we will be discussing in this lecture. So, imagine a situation that suppose this quantity beta 1 divided by beta 2 sine theta I, if this becomes greater than 1, and which can very well happen for a given value of theta I will have a certain value for sine theta I, and if the medium parameters were such that beta 1 by beta 2 with sine theta I, that quantity is greater than 1, then this sine of theta t will be greater than 1. What that means is there is no physical angle theta t for which this condition is satisfied. Now, this angle which we have got sine theta t, that is the direction of the wave propagation. So, what that means is that if this condition is satisfied, that beta 1 sine theta I upon beta 2 is greater than 1, then there is no physical angle in medium 2, that means there is no wave nature remaining in medium 2, because there is no direction in which the wave is propagating. This angle is an imaginary angle. But for this angle also the phase condition is satisfied. So, whatever fields we have written, they will still satisfy the boundary conditions. Only thing is there is no direction in medium 2 in which the wave is propagating, and that is a very interesting case. So, if I have this condition satisfied, then sine of theta t is greater than 1. So, there is no physical angle theta t. So, if we take this condition, then we note that since this quantity beta 1 upon beta 2 sin theta is greater than 1, and I require in my reflection coefficient expression a quantity which is cos of theta t, this we can write as square root of 1 minus sin square theta t. I can substitute for sin of theta t from this relation. So, from here I can get square root of 1 minus beta 1 upon beta 2 sin square theta I Since this quantity now is greater than 1, that is the condition we are talking about in this particular case. So, this quantity will be always negative. So, this quantity will be always imaginary. So, what I can do is I can take the imaginary constant j explicitly out of this, and I can change the sign of this terms inside the square root bracket. So, this we can write as j square root of beta 1 upon beta 2 sin square theta I minus 1, where this quantity now is a real quantity, because beta 1 upon beta 2 sin beta 1 square upon beta 2 square, sorry, should be squares. So, this quantity is greater than 1. So, that is why this quantity is positive. So, this total square root is a real quantity. So, cos of theta I is an imaginary quantity. So, we see in this case this quantity cos of theta t, that is purely imaginary. So, sin of theta t for this case is greater than 1, cos of theta t is purely imaginary. Both essentially are telling you that there is no physical angle theta t in which the wave will be propagating. However, as we have said that for this angle theta t and theta I still will be having the reflection and transmission coefficients. So, I can now go back and substitute these values cos of theta t in the reflection coefficient expression, and we have seen the two reflection coefficient cases. One was the perpendicular case for which the reflection coefficient was given by that, and we had a parallel case for which the reflection coefficient is given by this. At that time we had pointed out that essentially it is the interchanging of this eta 2 and eta 1, otherwise the expression for the two polarization is similar. So, for parallel polarization is eta 1 cos theta I minus eta 2 cos theta t, whereas for perpendicular polarization is eta 2 cos theta I minus eta 1 cos theta t. So, in both these expressions, if I substitute now for cos theta t, which is a purely imaginary quantity, the reflection coefficient terms they become complex. So, I can write explicitly for these two cases. So, I get from here the reflection coefficient for parallel polarization and that will be gamma parallel, that will be equal to eta 1 cos theta I minus eta 2 cos theta t upon eta 1 cos theta I plus eta 2 cos theta t, and if I substitute for cos of theta t from here, this will be equal to eta 1 cos theta I minus j times eta 2 square root beta 1 square upon beta 2 square sin square theta I minus 1 divided by eta 1 cos theta I plus j times eta 2 square root of the same quantity, which is beta 1 square upon beta 2 square sin square theta I minus 1. The similar expression we will get for perpendicular polarization also is simply eta 1 and eta 2 interchanged. So, the important thing to note here is that this expression is of the form A minus JB divided by A plus JB, where A is this quantity, in this case eta 1 cos theta I, and B will be the quantity eta 2, and this with the square root of beta 1 square upon beta 2 square sin square theta I minus 1, and A and B are the real quantities in this case. So, the important thing to note now is that this quantity always has a magnitude which is 1, because the magnitude of the numerator is square root of A square plus B square, same is true for the denominator. So, this will be always having a magnitude which is 1 and an angle which will be tan inverse of minus B by A, 2 times of that. So, that will be minus 2 times tan inverse of B by A. So, since the modulus of reflection coefficient is 1, whatever power is incident on the media now is fully reflected, because magnitude of reflection coefficient is 1. As we have seen earlier, this tells me the reflection coefficient of electric field, that means the amplitude of the electric field of the reflected wave with respect to the incident wave, and Poynting vector is proportional to E square. So, the reflection coefficient square if I take, that is proportional to the Poynting vector. So, this quantity if its magnitude is 1, that means the Poynting vector is relative Poynting vector with respect to the incident wave, that is now 1. That means whatever power is incident at the dielectric interface, the entire power now is reflected back into medium 1. Now, this was a very special case, because we have not seen this case earlier. Whenever we talked about the reflection and refraction in the previous cases, we had a reflection coefficient which was always greater than 0 and less than 1. So, we had not seen a case where the reflection coefficient is either 0 except when the two media are same, or the reflection coefficient is 1 when the entire power is reflected. So, in this case, even if we have a dielectric boundary, we get the entire power reflected back in medium 1, of course with a phase change which is given by this. So, since there no power transmitted to the second medium and the entire power is reflected back in the first medium, this phenomena is called the total internal reflection. So, this quantity then gives you what is called total internal reflection. So, as I mentioned, this condition is satisfied for even the perpendicular polarization, because you will have similar expression except eta 1 and eta 2 are interchanged. So, total internal reflection phenomena will take place for both polarization, that means for any arbitrary state of polarization. Then one can ask, what are the conditions under which this total internal reflection phenomena will take place, and what are the implications of this total internal reflection phenomena for the wave propagation across the boundary. So, one thing is very clear, if total internal reflection has to take place, then this condition has to be satisfied. That means beta 1 upon beta 2 sin theta I should be greater than 1. So, if I substitute explicitly for beta 1 and beta 2, essentially what we are looking for, a condition mu 1 epsilon 1 upon square root mu 2 epsilon 2 sine of theta I should be greater than 1. Now, since theta I can go maximum up to 90 degrees, that means this quantity is maximum value is 1. So, the condition under which the total internal reflection will take place or is possible when this quantity square root of mu 1 epsilon 1 is greater than square root of mu 2 epsilon 2. So, we want first a condition that if square root of mu 1 epsilon 1 is greater than square root of mu 2 epsilon 2, then there is a possibility of total internal reflection. That means then there is an angle theta I for which we will have total internal reflection. Then we can get total internal reflection. If you recall, this is the condition essentially same as saying that the medium 1 is a denser medium compared to the medium 2. So, when the wave goes from a denser medium to a rarer medium, then there is a possibility of total internal reflection if you launch the ray at an angle which is greater than certain value. For a pure dielectric, when the permeability mu 1 and mu 2 are equal, essentially this condition reduces to square root of epsilon 1 it should be greater than square root of epsilon 2. So, for non-magnetic material, mu 1 is equal to mu 2. So, we get the condition from here, it is square root epsilon 1 should be greater than square root epsilon 2, and we have seen square root epsilon 1 which is epsilon 0 into relative permeability for medium 1, and square root of that quantity is the refractive index of that medium. So, this gives me the condition N1 should be greater than N2, where these are the refractive indices of the two media. That is the condition normally we have talked about in our high school optics, that if the medium 1 is denser compared to medium 2, then there is a possibility of total internal reflection, and there we talked only about the refractive indices which was N1 N2, which was square root of relative permittivity of medium 1 and the relative permittivity of medium 2. However, now we know that the refractive index is not defined square root of epsilon R1, it is actually related to the relative permeability and relative permittivity. So, this is more like a general statement saying that if this condition is satisfied, then there is a possibility of total internal reflection. Now, at an angle when this quantity is equal to 1, that means the sine of theta t has become equal to 1, that means theta t has become equal to 90 degrees. At that angle we call the critical angle, and beyond which if the ray is launched, then there is no ray existing into the second medium. So, phenomena is here we are having medium which is mu 1 epsilon 1, here you have medium mu 2 epsilon 2, and if I launch a ray such that this angle is theta c, what is called the critical angle. So, at critical angle theta c, I have the equality square root of mu 1 epsilon 1 sine of theta I or theta c now critical angle, that is equal to square root of mu 2 epsilon 2 sine of theta t, which is equal to 1. So, the ray essentially is going in the direction along the dielectric interface. So, this is the dielectric interface. At the critical angle, the ray essentially travels along the dielectric interface. So, this angle theta t, which is equal to pi by 2. And as we mentioned here, beyond this, if the angle is increased beyond theta c, then this wave does not exist. So, we do not know what has happened to this wave. In fact, the angle theta t becomes imaginary. So, we do not know where that ray is gone, but systematically if I change the angle from 0 to theta c, systematically the refracted wave or the transmitted wave will change systematically from here up to pi by 2, and beyond that the wave nature in medium 2 will be lost. We do not know what has happened to that wave. So, at critical angle essentially this condition is satisfied, okay. And then that is what we had seen for the dielectric media when mu 1 is equal to mu 2, again we get the same condition for the refractive indices, that is n1 sine of theta c, that is equal to n2 or theta c critical angle is equal to sine inverse of n2 by n1. So, from this general derivation which we have done, we can get the special cases which we have been discussing in the past in our high school optics. What we had not discussed, however, then was that when the total internal reflection takes place, and if the angle is greater than critical angle, that will happen, the wave which is reflected undergoes a phase change. What we talked there only about the directions, and we said the whole power will be reflected, and that is what was the phenomena which was total internal reflection phenomena. However, now we want to see a little more deeper to this phenomena, and one of the important thing which we note here is that when total internal reflection takes place, we get a phase change abruptly at the dielectric interface. So, there is a phase change introduced between the incident wave and the reflected wave abruptly at that junction, which is the dielectric interface. And this quantity, since B and A are related to the angle of incidence and the medium parameters beta 1 and beta 2, essentially the phase change is a function of the angle of incidence and the medium parameters. So, in general, then we can say that by choosing appropriate parameters for the media and the angle of incidence, we can generate an arbitrary phase difference between the incident and the reflected wave. And this will happen for both the cases, for the parallel polarization and perpendicular polarization. However, important thing to note here is that for parallel polarization we have eta 1 here and eta 2 here, whereas for perpendicular polarization eta 2 is here and eta 1 is here. So, the two quantities B and A are different for parallel and perpendicular polarization. What that means is that the phase change which the wave undergoes for two polarization are different. So, parallel polarization undergoes certain phase change, perpendicular polarization would undergo some other phase change, but two polarization will not have the same phase change except when this quantity is 0. So, in general, then we can say that the first point we have seen that for having total internal reflection we must satisfy this condition. The second thing about total internal reflection we can now note is the wave undergoes a phase change at total internal reflection, and phase change is different for two polarization. Phase change is different for parallel and perpendicular polarization. If you write down explicitly the phase changes, I will get the phase change pi parallel, that will be minus 2 times tan inverse of eta 2 square root of beta 1 square upon beta 2 square sin square theta I minus 1 divided by eta 1 cos theta I, and phi perpendicular would be minus 2 times tan inverse of eta 1 square root beta 1 square upon beta 2 square sin square theta I minus 1 divided by eta 2 cos of theta I. So, this is second important thing, that the two polarizations do not undergo the phase change, as we will see later, will have the implications about the change of state of polarization when the total internal reflection takes place at the dielectric boundary. The third important thing is that when this condition is satisfied and cos of theta will be derived, is now given by this, which is purely imaginary quantity. I can now ask what kind of field variation we are going to have in the second medium. So, let us say we write the field expression. So, third thing, the fields in medium 2 as we have done earlier. This is the transmitted field which is having some amplitude E t, and we will have the phase which is minus j beta 2 x sin of theta I plus z cos of theta t is for second medium cos of theta t. This was the phase expression which we had for a transmitted wave in medium 2. This is the amplitude, and now what we can do is we can substitute for cos of theta t and in terms of theta I, and same thing we can do for sin of theta t also. So, we have got a condition from the Snell's law that beta 2 sin theta t is same as beta 1 sin theta I. So, this is E t to the power minus j. Let me first write down explicitly. So, this is x beta 2 sin theta t minus j z beta 2 cos theta t. So, if I substitute for cos theta t in this, then this is quantity is no more an imaginary quantity. So, it does not represent a phase. Of course, when we got here the square root sign here, we should ideally choose both the signs plus or minus and choose the sign appropriately, so that it correctly represents the field variation in the medium 2, and it will become clear what should be the sign chosen, so that we get the correct field variation. So, if I substitute now for sin theta t and cos theta t, this will be E t e to the power minus j, and this is beta 1 sin theta I. So, this becomes x beta 1 sin theta I, and this quantity will become plus minus. I substitute here for this, so that will be z beta 2 square root of beta 1 square upon beta 2 square sin square theta I minus 1. I can take this beta 2 inside to simplify, but the important thing to note here now is that this is the term which is representing the phase, but this does not have any phase. It is showing you now the variation of the amplitude of electric field as a function of z. That means, as I go deeper into medium 2, the field is not only getting change in phase, but also its amplitude is going to change. Now, since this quantity is real quantity, either depending upon the sign which we choose here, either positive or negative, either this field will grow exponentially as we go deeper inside the medium, or it will die exponentially as we go deeper inside the medium. Since the energy source is coming from medium 1, which is the incident field, there is no possibility of this field growing indefinitely as we go inside the medium 2. So, the positive sign is not the appropriate sign, because it will tell me that the field amplitude has grown to infinity as we have gone deeper infinitely inside medium 2. So, we should choose appropriately the sign which is the negative sign, which correctly represents the field which are exponentially decaying field inside medium 2. So, what from here then we get that the amplitude term now is original amplitude times e to the power minus z, and let me take this beta 2 inside. So, this is square root of beta 1 square sin square theta I minus beta 2 square, and the phase term e to the power minus j x beta 1 sin of theta I. So, the fields are exponentially dying down as a function of z, and they are having a phase variation now only in the direction x. What does it mean? It means that this term, when we combine with time phase, which is omega t, gives me a travelling wave nature only in the x direction, and there is no travelling wave in z direction. Earlier, if we start from here, as we know, if I did not have total internal reflection, it has the phase variation in x direction, it has a phase variation in z direction. So, we had essentially a travelling wave nature in both the directions x and z. However, now we see that the travelling wave nature is only in x direction and the fields are not travelling in z direction. So, this one essentially represent the decaying fields, and this term gives you a travelling wave in x direction. If I plot this field in the medium, the situation is like this. This is your dielectric interface. Let us not worry about how the fields are going to be in medium 1, we just focus only on medium 2. I had certain value of the electric field at the interface, and now this field is exponentially dying down as we move deeper in z direction. So, this is the electric field value, and this variation decaying field in z direction are travelling in x direction. So, this is the direction in which the fields are going to travel, in the x direction. Also, what we note from this expression is when these two terms are equal, and that is the condition corresponding to the critical angle condition, the field does not die down exponentially anymore. So, the amplitude of the field remain constant in medium 2. Again, it is not travelling, but the amplitude of this field is remaining constant in medium 2. So, at critical angle the field remains constant. So, this is theta is equal to theta c, and as I increase angle theta beyond theta c, the decay of the field becomes more and more sharper. So, this is, you may have field decay which will be like this or which will be like this. So, here I have theta 1 greater than theta c, this is theta 2 greater than theta 1, and so on. So, as the angle of incidence increases more and more beyond the critical angle, the field essentially get more and more confined towards the dielectric interface. So, you get here the field which are getting more and more confined because this function is dying down more and more rapidly. So, at critical angle the field essentially extend up to infinity with a constant amplitude, and as we go beyond the critical angle then the field start getting more and more confined towards the dielectric interface. But the important thing is that in no situation the field will go to 0 in medium 2. This field will be always non-zero in medium 2, and theoretically whatever small amplitude it is, these fields will be extending up to infinity in the direction z. So, when the total internal reflection takes place from medium 1 at this interface, when we earlier talked about total internal reflection at high school level, it used to give an impression when the entire power is reflected in medium 1, nothing exists in medium 2. And in fact, there was no description at all about what are the fields or what is the behavior, what is the role this medium 2 has to play in total internal reflection. Once we have this critical condition satisfied, can we remove the medium from beyond this point? Now, the answer is no, we cannot do that, because these fields which require continuity at this point and a functional form which is like this for total internal reflection are as important as the fields in this region. So, when total internal reflection phenomena takes place, we always concentrate only on these fields which are in the region where total internal reflection has taken place, but the field in the second medium are as important as these fields, because these are the fields which are supporting this total internal reflection phenomena. If any disturbance is created to these fields, the total internal reflection phenomena also will be disturbed, and there will not be total internal reflection, there will be always power which will be flown to medium 2. So, therefore, now it is important that if we wanted to have a good total internal reflection phenomena, firstly we must have these fields as confined to the media interface as possible. That means, we must launch a wave with an angle which is as larger compared to critical angle as possible, so that the field die down very rapidly. Secondly, we must provide certain region from the dielectric interface, ideally up to infinity, but in practice it will never happen. So, certain region beyond the dielectric interface where these fields are protected. If that condition is guaranteed, then we will have a total internal reflection phenomena in medium 2. Otherwise, theoretically, unless I provide an infinite medium here and these fields properly protected, we cannot have an ideal total internal reflection phenomena. So, we have important conclusions that when the total internal reflection takes place, these fields exist. That means the transmission coefficient is not 0. So, you should also note important thing that when the total power is reflected, the mod of reflection coefficient has become equal to 1, does not mean that the transmission coefficient has become 0. You may still have transmission coefficient, okay, which is non-zero, but this transmission coefficient does not always mean there is a power flow in the medium 2. So, as we have seen, these fields which are dying down here are the one which do not constitute any power flow, because the wave is not travelling inside the medium, the wave is still travelling in this medium along the interface. So, there is no power flow in the z direction, but the fields exist. So, we should very clearly understand the difference between having fields and no power flow and having fields and having power flow. We may have the electric and magnetic fields and they may constitute a power flow, as we have seen in the earlier cases. However, we may have a situation like this where we have electric and magnetic fields, but there is no power flow. In electrical circuit terminology, we can call these fields then like reactive fields, that they have the energy stored in this and no net power flow, but this energy is stored at least in the transient phase when the fields were getting set up. So, the picture one can imagine visualize is as follows: when the wave is incident on this, in the transient phase, when the waves are getting set up, there is some power flows to the second medium. That power flows gets stored in the energy in the second medium in these fields, which are decaying fields. And then once these fields are set up in the steady state, there is no net power flow into the second medium, and then the power flow essentially is medium 1. These fields then are also referred as the evanescent fields. So, these fields are reactive fields. So, these fields will exist in medium 2, only they will not constitute any power flow. The power flow will be along the interface, because in that direction there is a travelling wave. Now, what is happening in medium 1 now? We had a wave which is incident in this direction, and then we had a reflected wave which came here. The 2 reflection coefficient is now 1, and there is an arbitrary phase change at this point. So, if I look at now the fields in medium 1, field in medium 1. So, I have EI, that is amplitude EI, e to the power minus j beta 1 x sin theta I plus z cos theta I, and reflected wave ER, that is ER e to the power minus j beta 1 x sin theta I minus z cos theta I, because now the wave is just travelling backwards compared to the z axis. So, that is why we have negative sign, and as you have done earlier, we can write down these electric fields. Total electric field then in medium 1 E, that will be sum of these two, and now ER, mod of ER is same as mod of EI, because the reflection coefficient magnitude is 1 at total internal reflection, only thing it has a phase change. So, we can write this quantity ER is equal to EI with some phase change. So, let us say e to the power j phi, where depending upon the polarization this phi could be parallel or it could be phi perpendicular. So, I can write here. So, this will be your EI. This term is same. So, I can take it common. So, this will be e to the power minus j beta 1 x sin theta I one, this quantity e to the power minus j beta 1 z cos theta I plus 1 e to the power j phi, so e to the power j phi e to the power j beta 1 z cos theta I. If you now recall this term, or no, the amplitude is equal to 1. So, this is a standing wave, there is a phase difference here. So, depending upon the phase difference, what will be the amplitude at z equal to 0, that will change, but this is always going to create a complete constructive or destructive interference. So, these terms are identical to what we have seen in transmission line case when the reflection coefficient was equal to 1. So, when if the element which is terminating in transmission line is reactive, it used to have a phase of the incident and reflected wave, but these two amplitudes for the two waves were equal, and that is why we had a complete constructive and destructive interference. So, this one essentially now is representing a fully standing wave, and this term is representing a travelling wave. So, in medium 1, if I look at this phenomena of total internal reflection, what is going to happen? We will have a fully developed standing wave in z direction, but a travelling wave in x direction. When I look at this phenomena in medium 2, it is exponentially decaying fields in medium 2 and a travelling wave with the same phase constant beta 1 sin theta I in the x direction. So, if I plot this now, how the fields will look like in the two media, and let us say this is z direction. Now, depending upon the phase of the reflection, I may have a certain value for this quantity at this point, let us say it is this, and then I have fully standing wave. So, I may get the field variation which might, let me take a little small value here. So, here and from the continuity of the field just inside this dielectric interface in medium 2, the field are same, but they are exponentially dying. So, you will have exponentially decaying field on this side. So, if I now look at the field distribution, the field distribution will be like a corrugated surface in medium 1, a exponentially decaying thing in medium 2. But what is the constant phase plane now? The constant phase plane is decided by only this term. So, the constant phase plane is the YZ plane. So, now the important thing is that the constant amplitude planes are these planes, just where the amplitude is constant, but the constant phase plane is this plane and the wave is travelling in this direction. So, this very complex amplitude distribution of the wave travels in the x direction with this, with a phase constant which is equal to beta 1 sine of theta I. If I want to see now the total picture of total internal reflection phenomena, essentially whenever total reflection phenomena sets up, you have this complicated distribution created, the amplitude distribution in the space. On one side you are having exponentially decaying field, other side you are having standing wave kind of fields, and this amplitude distribution travels in this direction like this with a phase velocity which is given by that. So, this phase constant essentially will give me the phase velocity along x direction, that will be omega divided by beta, which is beta 1 sine of theta. So, this is the phase velocity along the x direction. So, now if I ask which direction the net power flow is, these fields do not constitute any wave. So, there is no power flow in the z direction. If there is no power flow in this medium in z direction, there cannot be any power flow in the z direction in medium 1 also, because if the power had come in this direction and if nothing has gone in this medium along z direction, there is no way here to consume power. We are talking about a completely lossless media. So, that means whatever power came in this direction, the power essentially get reflected back. That is what these standing waves are showing you. So, the fully standing wave nature essentially tells me that there is no power flow perpendicular to the interface. Along the normal, if I calculate, there is no power flow here, but there is a power flow along the interface. You are having a phase velocity, you are having a travelling wave. So, when the total internal reflection phenomena takes place, the net power flow is along the interface, or in other words what we are now seeing is this dielectric interface is capable of guiding electromagnetic energy. We can make use of the dielectric interface for guiding the electromagnetic energy along with them. Precisely this is what is used in the structure what are called the waveguides, and especially when we talk about dielectric media, this is what happens in the optical fibers. That optical fiber is nothing but a structure which is having a dielectric interface, and that structure, if I consider optical fiber like this, I have some refractive index here N1, another refractive index here N2, and N1 is greater than N2. So, if I now consider a electromagnetic wave launched at an angle like that, and if this angle is greater than the critical angle theta, greater than theta c, then there will be total and internal reflection phenomena in this medium. The field outside this will be exponentially decaying, and the net energy flow will be along the interface, along this direction, the power flow. So, if I create some structure like this which is optical fiber, it can carry the electromagnetic energy over a very long distance without any loss as such, because this is a total internal reflection phenomena. So, energy is confined to this region and it can propagate along this for a very long distance. So, total internal reflection phenomena has played a very important role in the modern optical communication, right, where in the design of the structure what are called optical fibers.